Alright, where were we? I think we were in the middle of writing this make file, which was a distraction from writing the file IO program using the C standard library. So the one more thing that we need for this make file is we need a .phony rule, or .phony directive, where we mark all and clean as not being actual files that we're trying to build. Once we've done that, then if we type make, it'll go ahead and build our C standard binary, and it's slightly worth taking a look at why that worked in the make file, just because I sort of did a shortcut make file here. So the GNU make program actually knows how to build a whole bunch of stuff. It has default rules that let it do that. So for example, we see that we told it that we wanted it to build a file called C standard, an executable, and we gave it the rule that it could build a file called C standard from a file called cstandard.c, and it knows how to build an executable from a C file, so it went ahead and used this default rule to do that. Now the default rule ended up being 2 steps, which is a little bit weird, where it built an object file and then removed the object file after it did a linking step. It used the default C compiler, which is called cc, and if we say what's cc, we find out that it's a symbolic link over to etc alternative cc, which eventually gets us back to gcc. But we can go ahead and say that our cc is gcc. We can say that our C flags are -g. And then if we do it, it's going to run gcc with the -g flag in order to compile, and so then we can do debugging. But that's enough distraction with trying to make fancy make files. The program that we're interested in is this file, or this program, which is going to output it's going to create a file called tempthing1, which we currently don't have. We run this program. Now we have a file called tempthing1. We do cat to view the contents of that file, and we discover that the text from that file is correctly the text that we output to it with our fprintf and opening and closing the file. So that's how we can create a file and write some text to it. If we want to read that text back in, we can do that by doing another fopen. And now instead of opening the file for writing, we want to open the file for reading. So we'll give it the string R. We know that to read one line of text from a file, we're going to use fgets. That's the command that we're also using to read text from the user when they type in the keyboard from like standard input. So we're going to go ahead and call fgets. It's going to take a string buffer, it's going to take a size, and it's going to take a stream. String buffer size stream. The stream is going to be input 1. We want to make sure that we close it when we're done. And so we're just going to allocate an 80 character buffer on the stack here. So then we're going to fget into the buffer. We're going to say the size of the buffer is 80. And then finally we can fprintf to standard out, which is just the same as printfing the text that we got read into the buffer. So we change this so we can run make again, we can run C standard, and it's going to print out hello thing 1 through this like slightly complicated process of creating a file, writing text to it, opening the file again, reading the text from it, and then printing out the result. So that's how we do sort of simple file I/O with the standard C library. I'm going to go through this again with sort of traditional Unix system calls or Linux system calls, which in this case is the same. In fact, the set of system calls that Linux implements for file I/O is specified by a standard called POSIX, which is sort of the like portable Unix specification. Was defined a long time ago and still specifies the sort of core set of system calls for a Unix-like system. So for this program, which we're going to call unix.c, because it's going to use the standard POSIX system calls, we're not going to include standard io.h because we don't want to use the C standard library for I/O. Instead, we're going to include systypes.h. We're going to include sysstat.h. We're going to include this thing. I think that's trying to say file control. Then we're going to include unistud, which is sort of the standard Unix system call header. And then there's one thing that we want to be able to do with the C standard library, which isn't about file I/O, but does involve me not wanting to have to write strlen by myself because it's in the standard library and it's simple. So now that we have our headers, we have a C program, and we're going to do the same thing as before. So we're going to say int thing1 is open. Let's make it a new file. Let's call this thing2. And now we have to go figure out what the open function is. So this is a system call. So we're going to say man2open to look in the section of the manual where system calls appear. And open takes a path name and flags, or it takes a path name, flags, and a mode. So it actually matters why there are 2 or 3 arguments here. Let's start off and see what flags are. So we have to bitwise OR together some flags. We need otrunc in order to get, if a file already exists, we want to truncate it to 0. We want ocreat right here, which is going to say that if a file doesn't exist, we're willing to create it. And then we want to say let me actually find where it says this. So the argument flags must include one of the following access modes: O read only, O write only, or O read write. So we're creating a file for writing, so we want O write only. Now instead of getting a file pointer here, what we get is a integer, so a file descriptor. And an integer file descriptor performs the same job in this sort of program here, where we're working with the like standard POSIX file I/O system calls that a file object or a file pointer served in the other program. So we open the file. When we're done with it, we still have to clean up after ourselves. For fopen, we fixed it with close. For fopen, we clean up with fclose. For open, we clean up with close. There really is a close system call here. It's pretty simple. It takes a file descriptor and it closes the file. So the message that we want to save is hello thing2 with a new line after it. Then we're going to use the write system call. We're going to write to file descriptor thing2. We're going to write the message, and then we're going to have the length of that be the length of the message. And this is, of course, why I included string.h up here. All right, so that is writing it to the file. Let's go ahead and do the same test. Thing2 does not exist. We run our Unix command. We look at thing2, it's there. We cat it, we get permission denied. Also, it's bright green. So this almost worked, except we have a slight problem. And let me show the problem in some more detail. If I look at all of our temp thing something.texts, the temp thing1.txt that we created with the C standard library ended up getting permissions of I, the owner of the file. I'm allowed to read and write the file. Other users on the system are allowed to read the file only, but they can't write to it. The permissions that I got for the file that I created with the system call are that I, the owner of the file, am allowed to write and execute the file, but I cannot read it, hence the permission denied error. And then other users on the system can do like random stuff, but not anything that makes any special sense. And the reason for that is because if we remember back here, man2 open, there's two variants of open. There's a variant where we only specify flags, and there's a variant where we also specify the file mode of a file if we create a file. And it turns out that in C, there's really not such a thing as overloading a function with two different arguments, or two different numbers of arguments. So when we call the open function here with only two arguments, what that means is that we're really passing it three arguments. And if we remember from assembly, the first argument goes in RDI, the second argument goes in RSI, and then the third argument goes in RDX. So if we don't explicitly specify a third argument, then whatever happens to be an RDX is what we get for our third argument, and what happened to be an RDX is whatever this mode is. So the way we specify modes is in octal, because we want to specify three parts. So we have permissions for the user, we have permissions for the group, user, group, and other. Each one of those things is 3 bits. Either it's executable or not, writable or not, and readable or not. And so if we specify the value in octal, every digit of the octal number is a number is an 8-bit value. Is a number between 0 and 7. So there are 8 possible values. To specify a number between 0 and 7, we need 3 bits. And so we can specify our permissions as an octal constant. A 0 at the beginning of the number indicates that we're writing down an octal constant. So the permissions that we want are, we want it to be readable and writable, but not executable for the user. So the first bit of the number indicates whether it's readable. The highest bit in a single octal digit is specified with the number 4. So the possible bits are the 4-bit, the 2-bit, and the 1-bit. Those are the 3 bits. So we want it to be writable by the owner. So 4 plus 2 is 6. We don't want it to be executable because we're not going to execute it. It's just a data file. So we're going to leave it as 4 plus 2 is 6 with no 1. And then for the other users, we want it to be readable but not writable or executable. That's going to be 4 for group, 4 for other. So we can specify our permissions as 0644. That's just how one traditionally specifies permissions for files on Unix systems. And now with that change, we're going to go ahead and explicitly remove the file, because if we are overwriting the file, we don't create it, so the permissions don't get specified. We can type make run Unix, and then we cat temp thing2.txt, and that works. We ls-l it, and it has the permissions that we wanted of rw, r. So there's a complication, but that's why we have to specify 3 arguments for open when we're creating a file. Next thing that we want to do here is create our 80-character buffer. We want to say we're going to open temp thing2.text for reading only. And because we're not ever going to create a file with this call to open, we can safely not specify a third argument. I can't actually do that way. This is a good example of where an inline comment might work, or a internal comment might be useful. So then we want to ask, we want to read from input 2 into the buffer, and read takes the size of the buffer and also the maximum length it's going to read. And another interesting thing about read is that it's going to return how many bytes it actually read. So the maximum size that we could read was 80, but if the file is smaller than 80, then we only read however much data we actually had in the file. So read is going to return that so that we know how big the thing that we wrote was. So then we can close input 2, and then we're going to go ahead and make sure that our buffer is null terminated. So we're going to say buff at the length is going to be 0. So the stuff that we read into the buffer is going to, let's say 10 bytes got read from the file. So that's going to be bytes 0 through 9 are data from the file. Length will come back as 10 because we read 10 bytes. So buffer index 10 is one space in the buffer after the last byte that we read in from the file. We'll make that a null byte. That's a null termination of our string. And then we can do a write to 1. Why are we saying 1 here? You should remember 0 is standard in, 1 is standard out, 2 is standard error. Always when a new process starts, we have the file descriptor table filled in that way. So 1 is standard out, which will print to the screen. We're going to print the buff, and then we're going to print we're going to write a number of bytes, the standard output equal to the length of the buffer, which we can ask for with strlen because we've null terminated the string. And with that, we have a complete file IO program. We can run make, we can do that, and we get the correct behavior here of printing out hello thing2 because we did a bunch of system calls to open, write to, open, read from, and then close files, and then write to standard output. Alright, so that's our first example program for today's lecture. I'll be back in a second with our next example program.